Hello everyone. Today we are going to study about the third chapter, and that is connected component labeling, distance measurement, Euclidean chessboard and city block distances, image acquisition and pre-processing, intensity transformations and spatial filtering. So at first we are going to study about connected component labeling. So what is connected component labeling is, it's basically, it identifies that what is the relation between the pixels and how the different pixels are connected together. So this is actually a very popular system if we want to work on real time in computer vision or many like OCR, object character recognition. So in that, how machines identify that a particular object coming in front of them is of what type. I mean to say that whether any image is there, or that is some character is there, or whatever information is coming from the image, how the system recognize that one, this connected component labeling. So let's see. So it has two passes, basically first pass and second pass. So first pass, the rule is always that you should always consider on the top, the first row and first column, the first element, you should always consider. It moves like this, from the top row to the second row to the third row to the fourth row. The processing actually happens like this, in this fashion. So for the first pass, what we are going to do, we are going to consider the top left. I mean, row-wise operation. This is the row-wise operation. Like this, we have to move. Then we have to move like this. Then continuously like this. Okay. So considering the first pixel, you can see that in the first pixel there is no top and left pixels, right? So if there is no top and left pixels, so what will be there? Here we have to write the same pixel. So this pixel is 1. Okay. For this pixel, what is there on the top and left side? The left side is actually 1. So if in the top 1 is there, means we can copy that one. In the left side, if any other pixel is there, that we have to check and we have to put. So if it is 1 here in the left side also, we'll be putting here 1. Then comes here, for this 0 pixel, you can see 0 pixel, we don't need to do anything. Okay, whatever is there, you have to leave it like this only. So we'll leave it blank. Then considering for this one, this for pixel 1, on the left side there is 0, on the top there is nothing. So in that case, what we have to do, we have to assign that a new pixel. Okay, so for that purpose we'll be assigning that it as a new pixel. So that is 2. Okay, then for this one again, on the top and left we have to see. So top there is nothing, but in the left we have 2, pixel number 2. So we'll be assigning that again 2. Okay, then here again you can see on the top there is nothing, but in the left side pixel number that is 2 is there, so we'll be assigning this 2. Then again for 0 we are not going to do anything. Then for this pixel again, you can see that on the top there is nothing, and in the left side also there is nothing. So that in that case we have to assign a new pixel, that will be 3. Okay, so for 0 we are not going to do anything, but like this we have to assign. Okay, then for this pixel, on the top there is pixel number 1, and in the left side there is nothing, so we'll copy the top, this one. So we are going to take this one. Okay, so we'll be considering this as what we'll be having here, 1. Okay, so let's keep it as a same color, so we'll take it 1. Okay, again for this pixel, what happens? For this pixel also, on the top and left there is 1 only, so we are going to keep it 1 here. Then for 0 we don't need to do anything. For this one, again on the top there is pixel number 2, so we have to keep in that case pixel number 2. Then again for 0 we don't need to do anything. Then for here on the top and left we have to check. In the left there is nothing, but on the top 2 is there, so we are going to put here 2. Then for this one we have nothing, in the left we don't have anything, but on the top we have 3, so we are going to have 3 here. Okay, then again we are going to go for this operation, and we'll be seeing for this pixel, in this pixel what is there. On the top there is 1, so we'll be straight away copying 1. So we'll be having 1 here, and same goes here, then same goes here. Why it is going, it's very clear to you, I think. On the top there is 1, left also 1, so 1. Here in the case top nothing, but left is 1, so we have given 1. Okay, then for this pixel, on the top we have 2, and here we have 1, so there is the conflict. Okay, So this conflict we should remember. Okay, here is the conflict zone. Here, here, if I want to put a pixel here, in that case on the top you can see there is 2, and in the left there is 1. So which one we'll consider? So we have a conflict here, right? So we'll just mark this one. So in this case, once you see that if you have two values, whether you have to take top or left, in that case you have to see the which is the minimum value. That minimum value you should take. Okay, so in that case we'll be taking what? We'll be taking 1. Okay, then next is 0, then after that 0, then after that 0. So we don't need to consider anything for this one. For then for this case you have on the top 3, so we'll be copying straight away 3. Okay, remember, if the conflict comes like this, we have to take the smaller value. Okay, again here completely we don't need to do anything because that is complete 0. But in this case on the top there is 3, so we'll be taking 3 here again. For zeros you don't need to do anything, we'll be considering that as a background. Okay, considering here in this case on the top there is nothing, left there is nothing. So in that case what will happen, we'll have to give the new pixel arrangement, and since 3 is already given, we'll be giving the new one, that is 4. Then for here also you can see that on the top there is nothing, but in the left there is 4, so we'll assign here 4. Here also 4. Okay, it will be keep on going till it's getting completed. Okay, so then there is 0, so we don't need to do anything. In this case of 1, again you can see on the top there is nothing and the left there is nothing, so in that case we have to assign a new value, and that is your 5. So let's take 5 here. So this is your 5. Okay, then coming here this is 0, so we'll not be doing anything. Then here in this case we have on the top 3, so we'll be taking 3. Okay, then in this case again 0, 0 and 0, so we'll not be doing anything. In this case you can see on the top 4 is there, so we'll be taking 4 here. Okay, so what is the color of 4? This is the color of 4, so we'll be taking 4 here. Okay, then comes here this place, here you can see there is 0, so we'll not be doing anything. But here on the top there is some number and the left side there is 0, so we'll be considering this as 5 only. Okay, then here you can see what will happen. In the top you are seeing you are getting 3, and here you are getting 0, so in that case you will be copying 3 here. Okay, then coming here we have again you can see on the top there is nothing. Actually you can see for this pixel there is on the top there is nothing and the left there is nothing, so in that case we have to assign a new pixel, and that is your, will be giving the new number as 6, because till 5 we have already completed. So this also will be 6, this also will be 6. Okay, because till here on the top there is nothing, in the left we have 6, so we have given 6. But here again the conflict comes. So what is the conflict? If I want to write here 6, we have to see on the top there is some number and the left also some number. So we can either write 6 here or 4 we can write. Okay, so as I told you, we have to always consider the smaller value, so because of that we'll be considering 4 here. Okay, then we have remaining 0, 0, 0, 4, 2, so 3 places will be 0. Then here again on the top we have 3, so we'll be taking this as 3. Again here you can see that again here there is on the top we have 6, so we'll be giving 6 here. So we'll be giving 6 here again. Then here also we'll be getting 6, because there is no conflict here. On the top also 6, left also 6, so 6. Here also we have on the top we have 6, and here also 6, so we'll be giving 6. Now again here is the conflict. Okay, so what we have to give? The left one or the top one? So what we'll be giving here is, we'll be giving here 4, because we have always to take the smaller value. So conflict is coming on which place? Conflict is coming again on this place. Okay, and also the conflict came here, right? So you can see these are the conflict zones. Okay, again here will be, we don't have anything because 0 is there, so there is nothing. Okay, then here you can see on the top and left there is nothing, so we have to give a new number, and that will be giving as will be giving as 7. Then again here on the top there is nothing, in the left there is 7, so we'll be giving here 7. Now again there is a conflict zone. So here either we can give 7 or 3, but since the smaller number we have to take, so we'll be giving here 3. Okay, so now you can say that this is also again the conflict zone. Okay, you don't need to put this conflict zone like circle, I'm just showing that so it will be easy for you to understand. So this was called pass 1. So pass 1 is completed. The blank space you can fill by black or whatever you want, because that is nothing but 0 values, and that will be considered. Then in the final labeling, the rules are pretty simple. In that rule, what you have to do is you have to only replace the temporary labels with the permanent one. So you can see that if there is 2 and 1, we have to take the minimum value, and in that case the 2 will be transformed to 1. Okay, and finally you will be getting that completely it will become 1, this completely will become 3, and this completely will become 4. Here you can see the conflict is in between 1 and 2. So 1 is equal to 2. Okay, then second conflict was in between 6 and 4. So 6 equal to 4. And we also had the conflict between 3 and 7. Okay, so in these conditions what we have to do, we have always to consider the smaller value. Okay, so in this case which one will take? In case of 1 and 2 we'll take 1. Okay, in the case of 6 and 4 we'll take 4, and in case of 3 and 7 we'll be taking 3. Okay, so wherever you are finding 2 you have to write 1, wherever you are writing 6 you have to write 4, and wherever you are writing, where you are seeing 7 you have to write 3. Okay, simple. Okay, so let's take the numbers. So this will be 1, 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 this will be 1. But again, as I told you, 2 is equal to 1. So what we have to do, this 2 also we have to write as 1. So 1, 1, 1, 1, 1. Okay, and there is no conflict. Yeah, there is conflict in between 3 and 7. So we will write 3 as it was. So we'll be writing 3 as it was. So this will be 3, this will be 3, this 3, 3, 3, 3, here also 3, continuously we are getting. Okay, now here instead of 5, 5 didn't have any conflict with anybody. So what we'll do, we'll write 5 as it was. Okay, so 5 will write as it was, and then we had the conflict with 3 and 7. So instead of 7 we have to choose 3. Okay, so we'll be writing here also. So this also become 3, and this also became 3. Okay, now there was any conflict in between 6 and 4? Yes, there was conflict in between 6 and 4. So wherever 6 was there, we'll write there as 4. Okay, so 4, 4, and instead of 6 there will be 4 only. So this also, this all will be your 4. Okay, so this is the final solution. Okay, so mainly how many colors are coming? 1, 2, 3 and 4. This is the final result. Okay, so you can say that we can fill this one with red color, this all red colors. Okay, and this will be your blue colored zones, and this will be your 5 color zone. So this is your final answer. Okay, so this is your the final answer about the topic. Okay, okay, so the applications are object counting, medical imaging, OCR, industrial inspections, whether the things are damaged or it's working correctly. So these are the different applications. Coming to distance measurement Euclidean, chessboard, and city board. So these are very important aspects of digital image processing, in that we basically identify that how much is the distance between different pixels, and you can say that on different objects in the real scenario. So distance measurement we are going to see today is Euclidean distance, chessboard distance, and city block distance. So let me explain you. Euclidean distance is actually the minimum possible distance. Okay. So for example, if there is a plane, it flies from Delhi to Mumbai. So what it will do? It will not move. It will not take zigzag paths. It will take the minimum possible way to reduce the fuel and reduce the distance. So basically, you can say displacement. Then chessboard distance. Chessboard distance, you know that how the king moves in the chess. Only one step, but in any one direction. Okay, diagonally or straight or whatever direction it is. So that is chessboard distance. And city block distance is nothing but like how we move our car in the streets. So this is also called as Manhattan distance. So in Manhattan, you can see that there are multiple streets. So in the streets, how you will move? You will go straight, you will take a left turn, you will again go straight, you will take a right turn, you will go backwards. So that type of movement is called as city block distance. The way the car moves in the city. Okay. So Euclidean distance is actually represented by dE, chessboard distance is represented by d8, and city block distance is represented by d4. So coming to Euclidean distance in detail, you can see it is defined by the straight line distance between 2 points. As I told you, it's the minimum distance, or straight line distance you can say, between the pixels. That is your Euclidean distance. Formula is root under x2 minus x1 square plus y2 minus y1 square, and where x1 and x2 are nothing but your points, and y1 and y2 are also the point in y coordinate, and x1 x2 in x coordinate. That will come. So interpretation, it's like measuring with a ruler directly between 2 points. Okay, so straight away. Use case, commonly in geometry, physics, and machine learning, this is used, especially in clustering. So it's like I have given one analogy, like there is a Superman. I mean, there is a this Superman actually flies from one place to another. So what the Superman will do? The Superman won't go left and right. It will The Superman will fly directly from one place to another to save the people. Same way it goes. So consider the case of this matrix. You know that all the images are considered in the case of in the form of pixels only. Okay. So we have considered this 5 and 6 you are seeing. No, these distances will find for all the cases. Okay. Moving forward, let's give some values. You know that in x coordinate and y coordinate, it can be represented as 0, 1, 2, 3. And in y coordinate also it can be represented in 0, 1, 2, 3. Okay, so it means what will happen? 5 is what? 0, comma 0. What is 6? Your 0, comma 1, 0, comma 2, 0, comma 3, 0, comma 4. Okay, then here what? This will come 1, comma 0. Okay, then 1, comma 1, then 1, comma 2, then 1, comma 3, 1, comma 4. So every pixel has a new number. So it means what? So what is 6? 6 is 4, comma 4. And what is 5? This is 0, comma 0. Okay, the pixel position of 5 is 0, comma 0, and pixel position of 6 is 4, comma 4. So we can also write this like m of x comma y is 0, comma 0, and n of a comma b is equal to 4, comma 4. Okay, so where n a comma b represents 6 and m x comma y represents 5. Okay, now we have to apply our Euclidean distance. So the formula will become a minus x square b minus y square. So where this is the position of your this one, right? 4, comma 4, that is n. So because of that only we are reducing. This is 4, comma 4 position, this is 0, comma 0 position, and we want to find a distance. This distance we want, Euclidean distance. Okay, so for that what will happen? 4 minus 0 of x value and 4 minus 0 of y value is your root under 16 plus 16 is equal to root under 32, and the value is 5.656. Okay, so it will be around 1, 2, 3, 4, 5. Okay, so this value will be there. Moving forward, we have chessboard distance. So chessboard distance is also very easy to understand. So chessboard distance is it's like the movement of king in chessboard as a square to move, right? So the formula is this one. You can see that maximum value of absolute value of x2 minus x1 comma y2 minus y1, whatever maximum value is coming for this calculation, you will be getting that answer. Okay, so interpretation is you can move diagonally so that distance is larger for horizontal or vertical distances. Use case useful in image processing when diagonal connectivity is allowed. Okay, so like the same way how the in the chessboard the king moves. Okay, so let's take the same pixel, I mean same arrangement of pixels, and you can see again the same numbering you're getting, just the formula changes. Okay. Now maximum value of a comma x comma b comma y. So 4 minus 0 comma 4 minus 0. So 4 minus 0 is what? 4 comma 4. Now the maximum value is what? 4. So now you can see the chessboard distance is actually nothing but you're getting the answer as 4. Okay. So the chessboard distance between all these three are 4, because it will move here, then it will move here, then it will move here, and straight away it will move here, right? So that is your chessboard distance. Then city block distance. Moving to the city block distance, you can see city block distance is like you're taking your car and moving in the streets. Okay, so it's also called as Manhattan distance. It is the distance traveled along grid lines like streets in Manhattan, and this is the formula: absolute value of x2 minus x1 plus absolute value of y2 minus y1. So interpretation is you can move only move horizontally or vertically, not diagonally. Okay, in the previous move you were moving diagonally. Okay, and here you are moving only horizontally. So in the use case, useful in pathfinding, robotics, and grip based games. In different games, like you remember there was a snake game in your Nokia mobile phones. In that you used to move like this. That movement was actually Manhattan distance movement. So like you're taking a taxi and you're moving in the street. Okay, so that will be your Manhattan distance. Taking the same scenario, let's change the formula this time. So we have absolute value of a minus x plus absolute value of b minus y. So we are getting here we have 4 comma 4, and here we had 0 comma 0, right? So that 4 minus 0, x value of this minus x value of this, and y value of this minus y value of this. Okay, plus. So you are getting 4 minus 0 is 4, and 4 minus 0 is 4. So that is 8. Okay. So if it has to move from here to here, it has to take like 8 steps. So what are the steps are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So like this it will move. Okay. Or it will move like this. Still it's 8 only. Okay. So like that. Okay. So that type of movement is called as Manhattan distance. So this is the combined analogy you can see. So what I see, like these are the different formulas for Euclidean distance, chessboard distance, and city block distance. So you can see that movement is allowed in straight line, in horizontal. In horizontal, here actually it's horizontal, vertical, and diagonal. In chessboard, in city block, we have horizontal plus vertical only. Okay. So you can see that these are the, like it's like ruler. You are putting a straight ruler, and here the king movement, and here walking streets of the city. Coming to the image acquisition and pre-processing, this is a very important step, and image acquisition is the first step in digital image processing. So starting that one, so we'll be going with the image acquisition processes. So you can see we have a camera, we are taking the photograph, and it's getting digitally converted. Okay, so how this happens? This can happen in many ways, and already we have discussed camera is not the only thing that can take the input images. Okay, there are many other options are also there, like X-rays are there, CT scans are there, sensors are there. So there are different things that can do image acquisition. Okay, so we'll be seeing everything in different steps now. Okay, so image acquisition is nothing but the process of capturing an image using a sensor, camera scanner, satellite, medical imaging system. Lot of possibilities are there. So what are the basic steps in taking image acquisition, taking the input image? Okay, first is sensing. It should have a light reflected from object is detected by a sensor. Same way as we see how we see some object. When the light hits something and the light hits to your eyes, you are able to see the things. The same goes with the cameras also. Okay. So because of this only, if there is no light in the room, you are not able to see anything, because there is no light to scatter and hit your eyes, right? Then we have digitization. So whatever is coming, that should be converted into a digital form, numerical format. So that is your digitization. and that is the base of your sampling and quantization. You already know the sampling and quantization, you have studied before. Now we have the storage. We have to save the image in some particular format to be used later. Okay. So these are the factors that affects the quality of image. That is resolution, lighting condition, and sensor quality. If your camera is better, it will be able to uh, get better quality of image. Okay. So now this can be done mainly with three different techniques. The first is a single sensing element. Based on a single sensing element, the information can be captured. And the second is sensor strips. With the help of sensor strips, it can be done. And third is your sensor arrays. With the help of sensor arrays, it can be done. So let's see how it's done in detail. So this is your image acquisition using a single sensing element. So single sensing element, you can see here, this is the box. I mean, housing is nothing but the box where everything is mounted, and there is the power in. Here the power is taken from, and here you have see the you can see that this is a voltage waveform output. So basically what happens, energy, I mean to say, the light actually falls on this one, and based on filter, it's able to filter the extra noise. And inside there is a film that basically film, you can say, or you can say that photodiode type of sensor. If the more light is falling on that, it will give you more value, more voltage. So that only is shown here in the form of graph. If light is energy is more, the graph will be higher. Okay, energy is less, the graph will be lower. Okay, and this is the, because of the sensing element is photodiode, it is based on more light and less light. So that's based on the intensity, it gives the higher or lower voltage. Okay, that's for example, you can say you have temperature sensor, no, like you have thermometer in home. So higher the temperature, higher the value, lower the temperature, the lower value, same way. Then we have line sensors. So this is series of the same type of sensors. Okay, so in a complete row, you will be able to get the values of each light source. Okay, if the light source is giving you less value, here you will be getting less. The more, the more. But this is happening for the if you can divide the image in the form of row and column. So this is happening for the complete row. Then we have your array sensor. So array sensor is nothing but, array sensor is the arrangement of this type of linear sensors, line sensors in multiple ways. So at the same time, you are getting x-axis and y-axis both. Okay, so that is your array sensing. Now we want the continuous images to be taken. Okay, in x-axis and y-axis also, two-dimensional images. Okay, so for that case, what we have to do, we have to have a moving drum. So this drum is actually keep on rotating. So when the rotation happens, every time the sensors will be capturing the information. Now this sensor is not only capturing the information on the point, but also for the different location of the drums. So whatever image you want to take, you have to keep it there. So when the drum rotates, it will be capturing the image on different places. Okay, so that is your combining a single sensing element with a mechanical motion to generate a 2D image. So what's the difference? Single sensor, it measures one point. Line sensor, it captures one row at a time. And array sensor, it captures the intensity. And moving sensor plus film, it builds the image line by line because of the movement. Okay, so examples are thermometer, document scanner, and your digital camera. You know, in the line sensor, you can see in document scanner, as it moves from the top like this, and again it comes back, and it captures everything. So that is the example of line sensor. Array sensor is your digital camera. At the time it flashes, it takes the input. Okay, moving sensor plus film, old style image scanners. Old time the scanners were there, no, they used to move and then they used to capture the information. So now we have strips. Okay, so a linear type of flat bed is there. On that, 4,000 plus sensors are deployed on different locations. So when the aircraft moves, imagine you are on an aircraft, and you are taking the video recording. So what will happen? As the aircraft is moving, you are able to capture the video of the place. It exactly does the same. The linear strip contains many sensors arranged in a straight line. The strip moves perpendicular across the area to be imaged. Okay, like to be imaged. Okay, each movement captures one line of the image. Okay, used in flatbed sensors, airborne imaging systems. On aircraft, we have this type of sensors only. This type of sensor strips are deployed to get the images clearly. So that this flat bed can have more amount of sensor. The numbers can be very high. So 4,000 plus sensors can be there to capture the detailed information. This is maximum used in your medical image processing, and you know that CT scans. So where the subject is inside, like this type of chamber is there, the patient goes inside and the camera starts to move, okay, around the head, and it takes the image. So that is the thing. An X-ray source rotates around the object. Sensor opposite the source detects X-ray passing through, and it's the medical imaging is the use like CT scan, you can say. Then in industrial imaging, where the camera itself moves and captures different location. So that is the same thing here. You can see that this is a linear movement. The object actually is kept inside, and this X-ray source actually moves continuously, and it will be able to. And sensors are actually fitted in this ring, and this image gets reconstructed, okay, and cross section images of 3D images will be stored, okay. So this is basically used to take the multiple images of the same object. So afterwards you can combine and you can make the 3D model of that. So this is very high quality thing. Now we have already discussed this image before, but straight away we'll be having it again. So as the light source falls on any object, it goes to image system, and image system takes the it basically fills the values like we did in the last time. So what it does, so as you can see, when the image value is if the light falls, start from here, the darker value is there. So what will happen, that that graph will go down. As it goes to the lighter value, the graph will go up, and those numbers are filled here digitally, and because of that you are able to get this digitized format. So sensor arrays are widely used in digital image processing to capture entire scene at once. Unlike sensor strips, the scan line by line, sensor arrays consist of 2D grid of sensors that record the full image in a single exposure, okay. So it basically is used to it basically does it really fast. So illumination source will actually give you the light. Then the scene is nothing but the object or area that we are going to take the photograph. Imaging system is nothing but a camera or scanner that receives light from the scene and focuses it on the internal image plane. Then projection onto image plane, the scene is projected onto a flattened surface, and digitized image is nothing but the 2D image that you are getting in. It has a length and breadth, and each sensor captures light density, and the result is digital image represented as a grid of pixel values, okay. So the pixel values are the important thing, because you are getting the digital values of that one, and image as well. So this was all about today's class. Thank you.